Okay, so maybe I should review a little bit about what a port is, just because we only went over it once. So the idea is that a port is corresponds to a driving point or an observation point. And so, for example, this point right here could be where we define a port. We have an applied external voltage, or force rather, and when this point moves, we get a velocity. And so we talk about the driving point impedance seen by this force at this port, at this driving point. And so what does it see? It sees a spring terminated by a mass. And so we talked about, parallel and series. So the spring compression force is exactly the same force that's driving the mass. So that's a parallel connection, common force. So the port is described completely by impedance ms for the mass in parallel with impedance k over s. All right. So that's assuming it's a linear time invariant system. And in those cases, we can describe a port by the port impedance. And so the port impedance is all we need to represent the system. And that means I could replace this with any simulator of that impedance, and the force would see the same load and behave the same. For any applied force, we get the same velocity at that point, at that driving point. So that's a port. And then when you make your equivalent circuits, you can formalize the series or parallel nature of it. And so here's the parallel case we just looked at. So now the port looks like two terminals, okay? We have our driving force, which is a voltage source in the equivalent circuit. And so it drives the port at two terminals. It applies a voltage. And then the current is whatever flows in. And so here it is, the parallel combination of K over S for the spring and MS for the mass. All right? And so we can talk about the port impedance and calculate it. So here's the port impedance using the rule for combining impedances in parallel. And so it's the product over the sum. And so it's a simple second order system. And we know that it was going to be second order because it had two energy storage elements, right? As long as one of them is not hidden, you're going to see a second order transfer function because you've got a mass and you've got a spring. Each of those is a first order system. And if they're not connected in some degenerate way, you'll get a second order system for the impedance.
Just kind of that in again?
Yeah.
Maybe something that we haven't covered about ports is that like when two ports are connected, they have to have the same port impedance by definition, or otherwise there's scattering that occurs.
Ah, yes.
So that's why you can say, let's consider the port impedance of force external and know what it is by looking at impedance it sees. So if we kind of chop force external out of that diagram and then look at what impedance there is between those two terminals without force external attached, that's why we get this port impedance. And then I guess one other definition that kind of is more of a general network theory thing rather than applied to acoustic or mechanical systems in particular is that at a port, and then this is kind of obvious from Kirchhoff's laws and such, but it's a definition. At the port, the through variable is going to be going into the positive terminal of the port and out, being velocity in this case or current for a circuit, and the across variable being force for mechanical systems or voltage is the drop from the positive terminal to the negative terminal. Did I just jump the gun?
Well, I just thought I would, well, I've already talked about this, but I just thought I would, go back to the general diagram of a port. So you have your applied voltage or force, and you have your resulting current or velocity, and then you have your impedance. But when I say gamma, then it's an admittance. And remember that gamma is more common if you want to think in terms of a transfer function, where the force is the input and the velocity is the output. Then the transfer function is V of S over F of S, and that's gamma of S. So impedance is force over velocity, and admittance is velocity over force. And if you think of the force as the input, then admittance is your natural transfer function. And that's what you see most often in the musical acoustics literature, the mobility or admittance measurements. And so we talked about the ports connecting them in series, meaning that their currents are shared, and connecting them in parallel, meaning they have a common driving force. And in this case, we're going to talk about, toward the end of the quarter, we're going to talk about wave digital filters. And in that case, we're going to go to another level. And we're not on that level yet. I just want to say, right now, we're not doing traveling waves. This is a scalar voltage that's applied and we get a current. But what we're going to do for wave digital filters is decompose the voltage into a left and right going traveling wave component. And when you do that, you get scattering. So these are two ports that have been connected together and they have two different impedances. So that means that if some force that's being, velocity or, force or voltage that's being applied to this, we'll see these as terminating impedances for a traveling wave. And that traveling wave is going to scatter based on the impedance seen there. And so wave digital filters are kind of on the next level. So the plan is, we're talking about just normal circuit theory where you say that the speed of light is infinite, the speed of sound is infinite. Another way of saying it is the wavelengths are very large. The wavelengths are much larger than the circuit dimensions. And so we don't have to deal with traveling wave notions at all. Everything's just scalar voltages and currents. And so we avoid all that. And that's what normal circuits do. That's what it's called lumped circuit modeling, where you have R's, L's, and C's. The frequencies in the circuit are low enough that you don't have to think about transmission line effects in the wires connecting the elements. So if an element goes up and down in voltage and there's a wire that connects it to another element, it is assumed that that element will go exactly up and down in phase. In other words, wires carry one voltage, and they instantly transmit that voltage from element to element. And that's what you call the lumped case. But the more complex case is called the distributed case, and it does happen in circuits, but they're like microwave circuits. So in microwave engineering, they're dealing with traveling waves in circuit wires. And so things aren't necessarily in phase. And you have to be really careful. How do you distribute a clock in that situation? How do you know that all of your elements are getting the rising edge of the clock at the same time? Well, you have to be really careful. If transmission line effects matter, you really you don't have that guarantee. So you will want to shrink the circuit down to where it's true, and that's why VLSI works. You can have a nanosecond clock cycle if things are just microns away. It works out. But transmission line effects are kind of the next level, and we're going to get there. But the way we'll get there is through when we're done with lumped modeling, we'll go to traveling waves and acoustic tubes. And that'll give us things like the speech model that I demonstrated on the first day that was done at Bell Labs. And we'll talk about modeling rooms and delay effects and different kind things like the Leslie, which is rotating horn and a speaker. And so you can think in terms of acoustic rays of different lengths and think of air as a propagation medium. But you do have traveling waves in that medium. And we'll do the string that way too. Vibrating strings will be thought of as traveling wave media. Same with wind instruments, and that's the efficient way to model those. And so once we've had our lumped modeling, and then we've had our distributed modeling in the acoustic domain, where it's really clear and intuitive. Traveling waves in air we're all kind of familiar with, right? They come out of speakers all the time and so on. Well, then we'll go to wave digital filters and pull it all together. And it'll be weird. I have to warn you, it'll be weird, but it'll be right at the end of the quarter. And it'll be a launch pad for real ongoing happening research. And Kurt's involved in this very, very heavily. And hopefully he'll share some of his most recently published results. And we'll talk about some of the latest papers in the field and so on. Because it's a happening research domain right now. All right, so that is the port view. So a port is a driving point or an observation point. Let me just mention that it's not where you put an actuator on one side of a system and an accelerometer on the other side. In other words, if you drive a system at one point and pick up something somewhere else, that's not the same. Your driving point's not the same as your observation point. So we don't normally define a port that way. That's an example of what you don't do. I mean, you'll still do that, but we'll have, in that case, just a transfer function from one to the other. But it won't have magic properties like being positive real. And that's where I'm going with this. So it turns out that every passive one port is positive real. And of course, I'm assuming linear time invariant. Let's see if I can actually get to that page now. Let's see. Okay, so you can imagine, you can believe that if I hook together lots of masses and springs and dash pots, I'm going to get some admittance, right? So here we have an nth order numerator and an nth order denominator. That could be, capital N masses and springs. And if there are no dash pots, then it'll be lossless. That means all the poles will be exactly on the j omega axis. And the zeros will have special properties that I'll tell you shortly. But if we have dash pots, then there'll be damping. And that'll pull the poles away from the j omega axis. And we'll have, a more typical system. It'll die out when you hit it. Now, normally this is done as a kind of approximation. So you can also just measure the impedance or admittance and then just fit a filter of any order you want. And in that case, you don't know what the masses and springs are exactly, but in some sense you designed a set of masses and springs that gives you a really good approximation to that system. So you can interpret your filter as the impedance of a mass spring network that's approximating it. But if you're in a situation where you just need that impedance simulated, you might not even really care whether there's a physical interpretation over here. You just want the right admittance, and you want it to behave the same way. Let's say it's a guitar bridge. You just want the bridge to respond with the same velocity at each frequency that the natural guitar bridge does. And that'll make it just do the right thing. It'll cause the same damping on the string as a function of frequency, and it'll cause the same transmission into the body of the guitar and then subsequent radiation into the microphones as happens in the real guitar. So in that case, it's just a filter design problem. And so you take your measured mobility and fit a filter with something like mfreq-z or LPC, whatever you want, really. Just go through the MATLAB toolbox, say help filter, and look at all the filter design capabilities in the filter design toolbox, which is extensive in MATLAB. And I do believe we have that. And just try things out and get good results and plug it in and you're happy. But you do have to be careful about one thing. If it's a guitar bridge and you're hooking up essentially an ideal string simulator to it, there's a very good chance that if you're not careful, the system will be unstable when you hook up your string to your bridge. And that's because if the guitar bridge is passive, and that means that this function here must be positive real. So essentially you need a filter design method that preserves the positive real condition. And we have a visiting visitor, I think he's coming shortly around April 20th or something. And he is Esteban Maestra.
He'll be here on Thursday.
He'll be in here on Thursday? Oh, that's great.
He'll be here for like 10 days.
Excellent. And he has developed a filter design method that preserves the positive real condition, and he's using it for modeling violin bridges and guitar bridges. So we'll get a seminar from him on April 23rd, I believe, maybe 24th. It's a Thursday, right after this class. And he'll show us his latest work, and it sounds great. I've heard the sound examples. They're awesome. They're really good. And it's a good example of a tour de force in this area of doing positive real bridge modeling and in 2 dimensions. So if you think about the bridge, normally for a violin, you just think about the rocking motion of the bridge. And so the string is primarily excited in the plane tangent to the bridge by the bow. But there's a significant component longitudinally as well, and he's modeling both. So you've got essentially 2 different transfer functions at the driving point corresponding to the rocking motion and to the vertical motion, and they sound quite different. If you go to a violin and flick the bridge sideways and then you tap it vertically, you can hear they sound quite different. Those are different transfer functions that mix together in natural performance. So So we're going to at least look at this one important property, which is the positive real property. Okay, so if a passive one port is positive real, and so what does that mean? Well, a complex valued function of a complex variable, call it gamma of s, could be some admittance, is said to be positive real if gamma is real whenever s is real. Well, that's no problem. Even our general filter design had that problem because we were using real coefficients. So that was going to happen. So the binding property is this one, that when the real part of the admittance is greater than 0, when the real part of s is greater than 0, the real part of the admittance must be greater than 0. Intuitively, as the real part of the admittance is greater than 0, meaning that it is net dissipative. Another thing you can see is that you get no contribution to the real part for just a mass or a spring. So what you're looking at here, you're looking for the damping. You're looking for the portion of the admittance that dissipates energy, which is its real part, and that has to be a positive real part. So that's intuitively what's going on here. Is we're just saying that the real part of the admittance is positive, meaning it is going to dissipate energy, it's not going to create energy. But there's some interesting mathematical implications of this. So when you write it down formally and investigate it, you get some interesting facts. So one, this is actually an equivalent thing. This might even be better as the definition, but you can show that if it's positive real, then the phase will be always between plus or minus 90 degrees. And hopefully I made that sound plausible by talking about combining springs and masses. What you should worry about is, what if you had two masses in a row? Couldn't you get 180 degrees phase shift? And the answer is yes, you're not allowed to do that. You can't do that. You have to alternate masses and springs in some sense. So you can't ever see a mass squared in some sense. So it's not like little transfer functions that you can string together any way you want. They must obey this positive real property, which means that the phase will be between plus and minus 90 degrees. And one thing you can say is that when the phase is at minus 90 degrees, you could say that the admittance looks like a mass, right? Because a mass is impedance ms, admittance 1 over ms, so that's a minus 90 degrees phase. So if whenever the admittance looks like it goes to minus pi over 2, you say it's acting like a mass. And when it goes to plus pi over 2, it's acting like a spring. And when the phase is 0, it's just a resistor, right? But it needs to be positive. So the real part needs to always be positive, and it can go to plus and minus 90 degrees, but it can't go outside of that range. So in other words, it's not possible to look like a mass squared, or two masses. You can look like a mass, and you can look like a spring, and you can vary in between those ranges, and that's all you can do. And that's all that will ever happen in a passive system. Okay, so here is an example of the lossless case where you have poles and zeros on the j omega axis, and so the poles are on the j omega axis without we expected, but why are the zeros on the j omega axis? Well, they have to be to preserve positive real. Because imagine we're starting at DC here, we're coming out of a 0, and imagine the graphical method for phase response calculation. So I'm here between this 0 and pole, and so I can see I've got a plus 90 degrees from the 0, and then I have a minus 90 degrees from a pole, but that's canceled by the plus 90 degrees from this pole, and then I can pair up these zeros and poles, and they just have canceling contributions, right? So I'm sitting here at a plus 90 from that DC 0, all right? And so here I am. I'm just coming out of DC with a plus 90 phase shift, and so I'm looking like a spring, right? This is the admittance, and therefore plus 90 is looking like a spring. Now, I can't hit another 0, because if I did, I would go farther up, and that would be out of bounds. That would be not passive. It would, and so I have to. So what you have to do is you have to hit. Since I came out of a 0, I have to hit a pole next. And what happens when you cross a pole? You get a sweep from minus 90 degrees contribution to plus 90. So it switches instantly from minus to plus. And so that means, and of course you subtract the phase of the poles, right? So that means a 180 degree phase swing. So that's going to take my pi over 2 and switch it down to minus pi over 2, where I look like a mass, right? So now I'm just on the other side of this pole, and that's where and that's where I look where it looks like a mass. We say the system is mass controlled. This is something from the acoustics world. They talk about spring controlled and mass controlled frequency ranges. So it's when the phase swings in the direction of that particular element. So as I cross this pole, I switch into the mass controlled regime where the system looks like a mass, looks like one mass as far as its phase is concerned. And then the next thing I have to hit is a 0. And that'll swing me back up to plus pi over 2, and it'll look like a spring. And then I'll hit another pole, and it'll look like a mass after that. So that's the way every lossless passive, it's not active. I guess it's passive. It's marginally passive, I will say. Passive corresponds to stable, right? So this system has no damping. It rings forever. If you pulse it, it'll just keep ringing at these pole frequencies forever. But if it's a driving point impedance or admittance, then it will have this interlacing property for the poles and zeros. The poles and zeros interlace along the j omega axis. And so when you make measurements of an admittance, you look for this. You make sure that it's happening and you enforce it. And the way you normally enforce it is you look at the phase of your measured mobility as a function of frequency and ensure that that phase lies between plus and minus 90 degrees. Now usually it'll be offset because you'll have some bad data at low frequencies and you have unwrapped phase. But once you take out the mean in a reasonable frequency range, then you can see it when it's centered about its variation. It's got a good plus or minus 90 or less variation. So that's one of the important properties of passive driving point admittances, like any guitar bridge, for example. And it's an extreme case with no damping, so you don't really encounter these cases, but that's the extreme case. Yeah, so here's the ring and mass impedances and why they have the phases they have. So now, there's a property of positive real impedances, passive impedances, that we'll use quite a bit, and that is if you reflect off of them, you get, in a case like this, you'll get an all-pass filter. So if this guitar bridge is sitting there like this with no damping, let's say this is the admittance of a guitar bridge, and I send a traveling wave in on the string. So the traveling wave comes in, and it's going to hit that bridge, and there's going to be transmission and reflection. But this bridge is 100% reactive. So it's got no energy dissipation properties. It's a purely imaginary reactance, we say, right? Reactance, susceptance. It's a purely imaginary thing. It's got a phase of either plus or minus pi over 2, and there's never, at any frequency, any dissipation. Well, there's clearly a loss at the zeros. So you do get these point losses, but the bridge generally does not accept energy. It only reflects the energy back at you with some phase, right? So it's an all-pass filter. It's an all-pass filter that's a little bit degenerate because of these zeros right here. So what you would do then is to make it well behaved, you would move the poles just a little bit to the left, and the zeros would also come off a little bit to the left. Introduce a little bit of damping, and then it's almost an all-pass filter. And in general, the poles are just anywhere they want to be in the left half plane, and the zeros are going to be still kind of interlacing because they're still going to have to, isolate the pole pairs from each other so that you don't go too far in one direction on the phase. So you still get these induced zeros in between the poles somewhere, roughly between wherever they are. And that's what you can think of as a sub-all-pass or a damped all-pass. That's an abusive notation. But it is a very well-defined function, and it's called a Schur function. So this function, the name Schur function has a long history in mathematics. You can find a lot of papers on Schur functions and their properties, and a lot has been done, a lot has been investigated. So, I think of it as kind of a damped all-pass. A Schur function is any rational function having a modulus not exceeding 1 on the unit circle. So its frequency response is less than or equal to 1. It's bounded by 1. You could say it's bounded by an all-pass. It's all-pass bounded. And this is the important property. And the way to think of it intuitively is that when you reflect off of it, the gain is never greater than 1 for any frequency. So imagine an incoming wave on a string. If it's tuned to just the right frequency that it reflects with gain, and let's say on the other side of the string we have a nut, a rigid termination, that's also perfectly lossless at every frequency, then the oscillation is just going to build up and up and up at that frequency. So we need the Schur function property for a reflection at the end of an ideal string. Same thing with an ideal tube. Let's say I have an ideal tube and I send a plane wave in, and then I cap my end of the tube, and then it hits some impedance. If the reflection is greater than 1 at any frequency, then that will grow, and the whole thing will blow up. It'll just keep growing without bound in the tube. And that never happens, and it never happens because all impedances that have no power supplies are passive, and that means their reflectances are Schur functions. So if there's no damping, they'll be all pass, but in the more general case, they'll be Schur. And so there'll be some attenuation or unit gain at every frequency, never greater than 1 gain. So passive impedances have Schur reflectances. This is just your first look at this. We'll be coming back to this over and over again. This is just like your first introduction to this. So here's the actual formula for the reflectance of an impedance R of Z, and this can be like our guitar bridge. And then we're coming from an impedance of R0. So a traveling wave is progressing through impedance R0, and it hits R of Z. So R0 could be the impedance of our string. We have this ideal string. I showed you last time that the impedance of a string is the square root of the tension times the density. It's the geometric mean of the stiffness and the massiness, the two resistances to motion. And so that's the wave impedance, meaning that if you send a traveling wave down, the force divided by the velocity is going to be that number everywhere you look. So a wave travels in some impedance. And so the voltage part equals the impedance times the current part. And so that is, and so as we've mentioned, that when the impedance changes, you get reflection, and this is the reflection coefficient. So if you're reflecting off of a complex impedance, some big one-port impedance, it can be any number of poles and zeros, then the reflection transfer function is calculated like this. And we're going to derive this. We're going to develop this stuff from the ground up. But right now I'm just going to give you the formula because it's worth memorizing. It's something you want to just go ahead and memorize because it comes up so often. So the way I think of it is the impedance step over the impedance sum. So it's how much you jump up divided by the sum. And intuitively you can think about it as, imagine you hit a brick wall. The impedance is infinite. Well then, these terms are dominating. R0 is small and finite, so you just get 1. Your reflectance is 1. And does that make sense? Well, yes, because we're talking about force waves. Force waves will reflect without an inversion. And I haven't really talked about force waves. Maybe it's easier to think about velocity waves, which are the opposite. So in a vibrating string, if you hit a rigid termination, it's clear that you're going to reflect with a sign inversion because the end of the string cannot move. So whatever velocity profile comes into the bridge, minus that must be coming out of the bridge in order to clamp it to 0. And force waves are the opposite. We'll talk about them later. Now for pressure, it's easy to think about. Let's say you have a pressure wave in a tube and it hits a rigid cap. You probably know just from basic thought experiments that that's going to reflect in phase. Right? The pressure is going to bounce off the wall and be a positive pressure is going to bounce off the wall as a positive pressure progressing the other way. Now an open end tube is the opposite. Pressure wave comes in, and there's the open end is said to create a node. So nominally we say the pressure is 0 in that open end. Now that's only an approximation. It's only 0 some fraction of a wavelength out of the tube. But to a first approximation you say that pressure is 0 at the exit of the tube. So the incoming pressure must be met by an opposite negative pressure. So the reflection is a minus pressure wave. So you get a negation in the open end. But that's the 0 impedance case. Well, let's plug that in. So let's plug in R of Z equals 0, 0 impedance. Then sure enough, we get -1 for the reflectance. So it makes sense. Infinite impedance reflects with +1 for a force wave or pressure wave in a tube. And a 0 impedance reflects with a reflectance of -1. And then the last case that's easy is if our terminating impedance is equal to the wave impedance, then it looks just like more string or more tube, and there's no reflection at all. And the reflection coefficient is 0. And you see the 0 right here. You get R0 minus R0. So that is the so-called matched impedance case. And this is what we do in our Ethernet wires, right? All of our Ethernet cables have these little terminators that are the same impedance as the characteristic impedance of the coaxial cable, so that the Ethernet doesn't have a lot of reflections. You want to send packets out over the Ethernet and have them not come back. You want them to progress, reach all the computers on the network and then hit their terminations and disappear. And we're definitely coming back to this. We're going to develop this for strings in detail, and then we'll also look at it again for acoustic tubes. And then we'll be looking at it again. We'll be looking at it in spades for wave digital filters, because you get this all over the place in wave digital filters where R of Z would be a port that you're connecting to, and you're coming from a port at R0, and so this is your scattering coefficient, and that generates what are called adapters in wave digital filters for hooking things together. All right, so that's the reflectance for force, and the reflectance for velocity is in some sense the dual, and so it's the it's the admittance step over the admittance sum, and that turns out to be minus the force reflectance. So the main thing I want to get across is that every passive reflectance is sure, where a passive reflectance is the reflectance of a positive real port impedance, which every passive one port is. Every passive driving point impedance has that property. Okay, so there we are. So now I'm going to show you this guitar bridging example, and hopefully you can appreciate it a little bit more. So I showed you the data already. Let's go jump back to that. Here's the measured data. Oh no, that's the synthetic case. So here's the oh, that's the coherence. That's the phase. Here it is. So here's the measured guitar bridge admittance, measured very carefully by Antoine Chen in his lab in Paris. And so we see a good measurement of the Himmel's resonance and 2 plate resonances. And way down here is just, probably the supports for the experimental apparatus. This low frequency resonance I wouldn't pay much attention to because there's nothing important going on in a guitar at 5 hertz. And so all this low frequency stuff is just stuff we're going to kind of forget about. We're just going to high pass this thing at around 50 hertz and work with the data above that and neglect everything below. Guitar doesn't need anything below 50 hertz, right? So that's our measured admittance. And then here is its phase. And remember, this has to be between plus and minus 90 degrees. So this is a nice check on your experimental apparatus. Now, sure enough, the low frequencies are not obeying the positive real constraint. So we don't know what's going on down there, but we don't care, so we're going to filter it away. But you do see that maybe we don't want to high pass at 50 hertz. Maybe you want to high pass a little bit higher. The lowest note of a guitar is around 80-something hertz. So let's go ahead and high pass down here, because if we do that, then we get a nice pretty phase curve varying in a nice range that's clearly within plus or minus 90. It's also pushing the limits a little bit because this is 100. So it's you can imagine if you go up 10 here, it looks like it's pushing the boundaries. So this would be, after the Helmholtz resonance, which is usually the most resonant mode in a guitar. In other words, when you knock on a guitar bridge, the last thing you hear usually is that Helmholtz resonance. That's the main air mode. That's the main breathing mode of the guitar body that's breathing out the air hole. It's like a big Helmholtz resonator, where the guitar body is the big spring of air, and the air in the sound hole is a big mass of air, and so that's your mass spring oscillator, Helmholtz resonator. And so above that, then it looks like a what does it look like, a spring or a mass? So we just crossed a mass. If we're looking at admittance, yeah, we are looking at admittance, and the mass is 1 over ms. So we'll be looking at minus 90 degrees. Good. So it's looking like a mass above the Helmholtz resonance. And then we hit a plate resonance, and it straightens it back out. And then we hit the 0 that we must hit. Or no, this must be the 0 that we hit, and then we hit the next plate resonance. Then we get a 0 in between, and then the next plate resonance. So that shows you the evolution of it, and the swing is quite dramatic. But it looks like it's, okay.
Sorry, can you tell us a bit more about the methods behind these measurements so that it's clear why we get this thing in the low frequency?
Let's see. I believe he used laser interferometry to measure the motion of the bridge, and I believe he hit it with a force hammer. And so you have to suspend, you have to hold everything, you have to put the guitar on some kind of structure. And that structure tends to have some low frequency vibration capabilities, like any table. And so you'll get some stuff down there. And it's not being excited and observed at just one point necessarily. So you can be getting contributions that are distributed, and then that will not obey the passive one-port impedance rules. So he's very careful to measure the motion in the same place that he strikes. But if there's other noise coming in from the whole system just shaking after the impulse has gone away, then then positive reality could be violated. But I would definitely have to think about it. It could also be that the level looks good enough. Oh, I remember, we should look at the coherence. So have you heard of coherence? The coherence function is a measure of how accurately you are measuring what you think you are measuring in the presence of noise. So I think I actually defined the coherence. So the coherence is defined as the cross spectrum over the cross spectrum squared over the product of the power spectra. So S of x would be the power spectrum of the excitation. That would be the force hammer pulse that went in. And SYY is the power spectrum of the resulting velocity measured by the laser vibrometer. And then the cross spectrum, we all know from 320, is the Fourier transform of the cross correlation. And so you cross correlate your input and output basically. And you also may remember that should be the impulse response. If you cross-correlate the input of a linear system with its output, you should see the impulse response as the result. So the Fourier transform of that would be the frequency response of the system, and then we're doing a magnitude squared of that. And then let's say our input was an impulse, that goes away. And what's SYY? Well, it's going to be the magnitude squared frequency response. So we expect 1. So the cross spectrum, the coherence function for a linear system should always be 1. Now, why might it not be 1? It might not be 1 if we don't excite all frequencies. Let's say we have a hole, let's say we have a null somewhere in our excitation. Then that's a 0 in the denominator. Who knows what's going to happen? Yeah, we should get a 0 in the numerator as well, but it's indeterminate. And if there's any noise whatsoever, you'll see it in the numerator, and you'll just get garbage, right? So there's sources of noise. You could also have noise in the output, and then you'll be dividing by something that is not seen. So that noise will not be correlated with the input, and so it will, the cross correlation will melt down, so to speak, at some frequency where there's too much noise, and so you'll get a drop in your cross correlation, you'll get a drop in your cross spectrum, and so you'll divide by this and get something less than 1. So you'll lose coherence when you have noise, and so here is our measured data. He did 3 measurements, and so these are actually overlaid. So you can see, if you look carefully, that there's more than one curve. And at the when you get to the upper plate resonances, and the measurements go on for many, many resonances, you see good overlay for the 3 independent measurements, but you do see them start to pull apart at the Helmholtz. Like there was one that was much ringier than the other 2. I don't know if you can see that in there, but there's a fair amount of variance. You do also see that the Helmholtz resonance is the skinniest peak. That means it rings the longest. That's the longest ringing peak because it's the thinnest. The decay time is proportional to 1 over the width of these things, right? And so all these other peaks are significantly broad or wider, and you can see that there's a progressive widening of the peaks as you go up in frequencies. That means in the time domain there's a progressively faster decay as you go up in frequencies. So the modes are decaying faster at higher frequencies, and this is something you see all the time. It's very, very typical of physical systems. You get more damping at higher frequencies. And the Helmholtz resonance is by far the sharpest, but you also have some variance there. And look at that low frequency stuff. There's a lot of variance down there. So they're not overlaying at all. There's a lot of variation there. And now here's the coherence function, and sure enough, it starts to lose before you get down to the Helmholtz resonance. And you see just a lot of loss of coherence here. This has been arbitrarily scaled, so I don't know exactly how far down that goes. But you can see that your good data is up here where you're pushing close to 1. You also have these little dropouts in the coherence, and those tend to be associated with zeros. So if you have a system that with a 0, then you're trying to drive that 0, and it's hard. And in this case, it's a mobility. So we have little mobility. That means we have a very high impedance. It means the system did not accept energy at that frequency. It means we got little to no velocity in response. So it means that the noise is significant, and we're not driving up above the measurement noise in our output. So that's a very typical loss. Now this one actually is not over a null. It looks like it's over a spurious, very, very thin resonance. So that might actually be some ringy noise, some vibrating system, something that's vibrating that's not in the guitar, that's contaminating the output. What else could that be? You could get a ringing in the force hammer itself. It's possibly a ringing, the first resonant mode of the force hammer itself, which is a piezoelectric crystal after all. And so that thing can actually ring. So if it had a resonance at 800 hertz, that would explain it. But that seems a little low. I think piezoelectric crystals have much, much higher resonances than that. So I would go looking for a resonance around 800 hertz and see what's messing me up here, and find it, damp it, redo the measurements. And it looked like it did affect, well, maybe it didn't affect all of them. Yeah, maybe not all of them. So maybe just, okay. So this is the fun thing about the experimental side, is that you get all these little glitches and stuff that you don't know, you have to go play detective and figure them out and check them down. All right, so that is the way that it should look. This is real measurement. And so now we can fit a filter to this, keep it positive real using maybe Esteban Maestra's technique, and we'll have a really nice physically modeled guitar body that is passive. We can hook it up to a good string simulator, and it should behave just right and do all the right things. Build ourselves a good guitar. All right, now I just want to give you a little bit of insight into positive real systems. Talk about how you can make one synthetically. Okay, so this is a synthetic example, not based on data, but it's inspired by that data. In other words, I've gone in, I've measured the modes, I know their frequencies and their bandwidths and their heights, and now I'm just going to build it. I'm just going to take a bunch of biquads and make that guitar bridge, and the only thing I'm going to do is try to keep the mode frequencies right and their bandwidths and then I'm just going to make sure they're positive real when I put them together. So how do I assemble biquads to make sure that they're positive real? And I've got two methods, and then we'll be done. All right, so let's consider the lossless case first. That's zero damping. Now that's a useless bridge because sound cannot come out of it. All of the energy will be reflected back on the string, but it's a good first approximation. At least have great sustain. If you pluck this guitar in a vacuum, it'll ring forever and ever and ever if the string is ideal. So the bridge is a pure reactance. And then the string body coupling will therefore be energy conserving. That means all energy will reflect back on the string. If we look at the admittance, we'll see all of the poles and zeros interlacing along the j omega axis with infinite Q. And so we'll see the same phenomenon of looking like a spring at DC, looking like a mass at infinite frequency, and alternating in between. So now, we know this, we've talked about this. Okay. So it alternates, so we know how that looks. We saw the diagram. So here's a way of ensuring that the impedance is positive real. We know that the reflectance is a Schur function, right? Well, solve for the impedance. So remember the reflectance, S, the Schur function, was R of Z minus R0 over R of Z plus R0. Well, solve that for R, and you get an expression in terms of the Schur function. It's easy to make a Schur function because it's just an all-pass that has a little extra attenuation. And in the lossless case that we're talking about now, it's just an all-pass filter. So S of Z is just any all-pass filter, and so we'll pick an all-pass filter with resonances in the right place. And we can then go through this formula and get a guaranteed positive real impedance, bridge impedance. So we know how to make all-pass filters. It's just you take any stable polynomial, any minimum phase polynomial A of Z, and flip it around backwards to get the numerator, and that's an all-pass filter. And we scale it so that it's less than or equal to 1. All-pass filters nominally have a unit gain, but we can make it anything less than 1 very easily by just introducing a coefficient. So that's one way to do it. Now method 2 is a little more accurate. It gives you a little more control. And that is you just use this alternating zero property to try to do the right shielding. So here's a biquad that's a 2-pole. So it's going to have 2 resonances. And they're complex conjugate pairs. And so we put a 0 right between them at DC and figured that might work, right? Because that interlaces. So we have a negative frequency pole, a 0 at DC, and a positive frequency pole. So that looks like it should be okay. And then we can control the bandwidth and center frequency, and we have to check to make sure that it's positive real. But it gives us more control. So, as I mentioned, Esteban has a way of doing filter design that guarantees positive real. It's actually very close to this method. He has just a different guaranteed positive real building block that he uses and does the design in terms of those blocks. So imagine this just being a building block that you find optimum linear combinations of. So then here's the MATLAB for method 1 and method 2. I won't drag you through the details, but it's there if you want to see it. And I'll just show you the results. So we are able to get the resonances wherever we want, but we cannot control their relative levels. And we have our alternating resonances and anti-resonances, as we know we must. And we look at the phase, and sure enough, it's in plus or minus 90 degrees. And so this has been slightly damped by G less than 1. And so it's physically viable. So we can hook up a string to this, it'll work, it won't blow up, and it'll have resonances, the right frequencies, but they're not quite right, but at least it's passive. Now here's method 2. There's the MATLAB. You can study it if you're interested. And in this case, we have much more control. So we now can get our Helmholtz resonance independently placed relative to the upper plate resonances. And so, so we get a much nicer, this looks closer to the data.
Why is it so wide, the Helmholtz resonance?
Why is it so wide?
Much narrower, you said it was like the one that brings the longest, right? So the plate modes are a lot more narrow.
Yeah, you're right. This is overdamped. It's an overdamped Helmholtz resonance. Yeah, so I would like to go back. I have control over that, don't I?
You should, right?
Right, because
Microns.
right. So I typed in the frequency. Look, I'm actually modeling that low frequency thing. I don't know why. So and it looks like now. So I've asked for a pretty high Q here. So this is a Q of about 5, right? And that is oh no, these are higher Qs. So yeah, this is actually just operator error. I've actually specified a higher Q for the higher resonances.
Okay.
So this is something that just needs to go be redone. I don't remember running into a problem. I think I just didn't really pay attention to the relative Qs. So that is something, that's just design error. We can fix that. All right, so I'd also get rid of this low frequency stuff, right? Esteban does it too. He just neglects it completely. Although he found that it's nice to keep it while you're modeling, because it does have an effect. When you pull it out, it can shift your higher response and introduce an error. So you want to fit everything and then drop it at the end. All right, and now we look at the phase and check and make sure we're in the range plus or minus 90 degrees. And if that's the case, so you can just test and make sure that it came out positive real by looking at the phase. And so that's it. And there's the measured case that we looked at and the overlays with the coherence. Oh, and this is now the phase response overlaid with the coherence. Here you get a nice overlay. They agree quite well. And I'm not looking at low frequencies here. And you just get little blips for the loss in coherence. So it looks like good data when you see an overlay this nice, 3 independent physical measurements. Also, it's good to look at overlays just to get a feel for what your variance is. So you can just eyeball this and see what your sigma is as a function of frequency. And you see where your problems are, see where divergences are. So, a lot of people like to average, and sometimes you'll have an average with a standard deviation. Why not just do the overlays first? Because, it'll catch things like outliers. If you have an overlay of various functions and there's one that's just way off base, you don't really want to average that in. So you really want to look at the overlay first. It's also called a scatter plot. You're just looking at raw data. You haven't averaged anything. And everything should line up on top. No matter how you excite the system and no matter how you measure the output at the same driving point, you should have the same frequency response, the same transfer function. So they should all overlay perfectly, right? Well, they won't. I guarantee you. I don't care what you're doing. Here, at least we're using the same method each time, and we get a good overlay. But it's just good to look at the raw data, all piled up, and then with your eye, determine what to throw out, and then average, and then once everything looks, statistically similar, then you average and get a standard deviation and error bars and that sort of thing. So don't forget your raw data inspection step. So, any questions, comments, considerations? We're all ready to go make a guitar. All right. So then next time I'm going to talk about state space because I think it's important.